screen is visible, right?
Yes, sir.
Okay. Okay, let us start. Welcome to another class of numerical analysis, and today's topic is solution of ordinary differential equations. Specifically, we'll be looking at first order differential equations, ordinary differential equations, of course. And let us begin without further delay. Here, we are going to be looking at mainly two methods. One is the simple forward Euler method, and the second one is sort of class of methods which are known as the RK method or Runge-Kutta method. And our starting point for today's lecture is this familiar flow diagram, which has been discussed quite a lot of time throughout this course. And we have come to know that the utility of numerical analysis or numerical methods is sort of in the phase where we have already got the mathematical model and we are looking at trying to solve those mathematical models, those abstract models. Now, mathematical models could be in terms of mainly equations, different types of equations, such as nonlinear equations or linear simultaneous equations or differential equations, which may include partial differential equations as well as ordinary differential equations. So solution of these different types of sorts of equations are usually the field where the numerical analysis plays a part. Previously, we have already talked about and in quite a bit of detail about solution of nonlinear equations as well as solution of linear simultaneous equations. And today, we shift our focus to solution of ordinary differential equations or ODEs as they are known in short. So what are ordinary differential equations? They are basically a relation between a function, the derivatives of the function, and the variable upon which both of these, that is the function and its derivatives, depend on. So it's a relation between a function, its derivatives, and the variable upon which they depend. And mathematically, it can be expressed like this. So f is the function, and you can see that function is dependent on x, y, also y dashed, y double dashed, going up to ym. Here, by the way, m is not a power, but it is indicative of m number of dashes. That means it is the mth derivative. Y dashed, of course, is the first derivative. That is, it is represented as dy dx. Y double dash is d2y dx2, and so on. So obviously, ym would be dmy dxn. Here, m is the highest order of the derivative that is present in this relation. Needless to say, both y and its derivatives are here functions of x. Here we know that order of the ordinary differential equation is obviously the order of the highest derivative. So in this case, if m is the highest order, then the order of the ODE would be m. And the degree of ODE is the degree of the derivative of the highest order in the equation. For example, we can look at this sort of a system or this sort of an equation. So where dy dx is given by f of xy, where f of xy could be a general nonlinear function in x and y. Or it could be also a set of tabular values. From our previous understanding, we know that functions can also be represented as tabular values. So this particular function fxy could be a general nonlinear function or a function which is given in a tabular format with discrete values of x and y. If we talk about specific examples, then you can see the examples of the nonlinear function as fxy is given by a product of x and y. So the first equation here is dy dx plus xy equal to 0. In the second equation, we have another nonlinear function as f of xy, that is dy dx is equal to x square plus y square, which is quite obviously a nonlinear function. Both of these equations, which are given as specific examples, are first order systems. And the next equation that we will consider is a second order system. As you can see here, a second order derivative is present. So d2x, dt2 is present here. And as a result, it becomes a second order equation, second order ODE. If you are interested, you can probably take this note that this particular system is basically a representation or equation of motion of a vibratory system. Let's say we have a mass m like this attached with a spring and a damper. So this is the spring stiffness K, damping coefficient C, and it is connected to the ground. If this mass is set in motion by providing some displacement to it, then it is going to vibrate about its equilibrium position, which is somewhere around here. And that motion is in fact modeled by the differential equation given over here. So in real life, a lot of different systems, specifically dynamic systems, may be modeled, and their behavior is governed by sort of ordinary differential equations. So solution of these ordinary differential equations is a very important topic. Now, what do we mean by this solution of ordinary differential equations? A particular solution of the ODE would be a relation between the variables y, x, and m number of arbitrary constants, which satisfies the equation. But of course, it cannot have any derivatives in it. So we have a general solution of an ODE, which is a relation between y, x, and the arbitrary constants. The number of arbitrary constants would be equal to m. But this relation should not contain any kind of derivatives. The solution could be in two different forms. One is implicit form and the other one is explicit form. As I was saying, the ordinary differential equations can have its solution in two different forms. This is that is really disruptive, you know. If I have to leave so many times to let somebody in, that disrupts the flow. Anyway, let us continue. As I was saying that an ordinary differential equation can have solutions in two kinds of forms. It can either be an implicit form, where you can see phi x, y, c1 going up to cm, where phi is a function, of course, is equal to 0. So the right hand side is equal to 0. And in the explicit form, y is expressed as a function of x and the different constants, the m arbitrary constants. And these solutions are usually obtained within a given range, where you can see that x varies from x0 to xf, where x0 is the initial one and xf is the final value. How about these arbitrary constants? How can we obtain the values for them? They can be determined from m prescribed conditions. That means the ordinary differential equation in itself is not enough. It has to be supplied with certain conditions. If those conditions are not provided, it is difficult to solve for the ordinary differential equations. And the given conditions could be like this. That is, yv at x0 is equal to eta v, where v varies from 0, 1, 2, and going up to m minus 1 at a particular value of x. Let's say at x equal to x0. So at a given value of x, at x equal to x0, we are provided with, let's say, y. This will be some value, say eta 0. We may also be given y dashed at x equal to x0. So eta 1, like that. Different conditions would be provided. So at a given x, values of the function as well as its derivatives are given going up to m minus 1. The conditions could also be provided at a different point, that is the final point. So instead of the values of the function and the derivatives being provided at the initial point, it may be also provided at the final point, where y at x equal to xf could be given as this. Maybe I write it as eta f. And other conditions for derivatives are also given. So these are the given conditions. On the basis of these given conditions, we are to solve the ODEs. Now, if the value of the yv's are given at x equal to x0 and the solution is required in a domain where x varies from x0 to xf, then it is known as an initial value problem. At the initial condition, the values are provided, and the problem in that sense is called an initial value problem. Its counterpart is the boundary value problem, where the yv's are given at the final value of x, that is x equal to xf, and the solution is required for x varying from x0 to xf. So that is the definition of a boundary value problem. In our course, at present, we are interested only in the initial value problem. Moreover, we will only be looking at first order systems. Which means that we'll have dy dx as the highest order of the derivative. So as we can see here, we are looking at numerical solution of first order ODEs with given initial conditions. Examples could be like this. So dy dx is equal to fxy, where fxy is a general nonlinear function or a tabulated value, with an initial condition of y equal to y0 at x equal to x0, which implies that y at x0 is given as y0. So the initial point, the starting point of the solution is given to us. And that point is in an xy plane, x0, y0. It's an initial value problem. And the solution that we obtain would be of this form, either in explicit form, where y is equal to g, that is a function of x and a constant c, or it could be in implicit form, where g as a function of x, y, and the constant c is equal to 0. So this is the definition of the problem that we are looking to solve in this class. First order systems of ODEs with given initial condition. Now, if we ask what is meant by the solution of a differential equation, physically, what does it mean? Mathematically, it's a function. We have seen it can either have an implicit form or an explicit form. But what exactly is its physical significance? We can answer that by saying that the solution is basically a curve gxy in the xy plane, whose slope at every point xy in that xy plane in the specified region or domain of x varying from x0 to xf is given by that ordinary differential equation dy dx equal to fxy. So basically, we are looking for a curve in xy plane. The initial point of this curve is provided to us through the initial condition. Remember that this is an initial value problem. So y equal to y0 at x equal to x0, this is given. So we know what the initial point is, and that point is x0, y0. Starting with this and the slope of the curve. The slope of the curve is also known to us. We have to develop a particular curve gxy in the plane xy, whose slope at every point in the specified region would be given by the ODE. So that is the physical meaning of the initial value problem. And the easiest way to do that is to extrapolate the values of y for a set of values of x in the range x0 to xf. Starting point is known, the slope is known at the starting point. So we extrapolate at certain different values of x within the zone x0, xf, and find out the values of y at those x values. Let's look at it graphically. Here we have the xy plane. This is the specified region or zone in which the solution is to be obtained. X0 indicates its initial point, whereas xf is the final point. So at this x0, we are provided with y0. So x0, y0 is known and indicated by this red dot. So that is the initial point. So that initial point is known. What else is known here? The slope at that point. How do we know that? Because we have the differential equation. Differential equation dy dx is equal to f of xy. So if I can put values of x and y in this function, I know the slope because I know dy dx. Dy dx basically is the slope here. So if I put x0 and y0 in this function, I'll get the slope at the initial point. I do not have any idea what the next point is, but I know the initial position of that solution and the slope. So what I can do is simply extrapolate it like this, extend the slope towards the final position xf, where it will intersect with its vertical line drawn through xf at a given point. Let's say that given point is indicated by the blue dot. This might not be the exact point, but of course it is an estimation. The exact solution could be like this, given by the green curve. But we do not have any kind of idea about the exact solution. That is why we are going for this numerical solution. If we can solve it through any kind of analytical method, we could have obtained the exact solution appropriately. But here, we are applying the numerical technique because we do not have any kind of idea about what the exact solution is. And in that scenario, any kind of estimate of the solution is good enough. So this blue dot, in fact, represents the value of y at the position xf. It, of course, has, if compared to the exact solution, quite a lot of error. This is an approximate solution after all. We know that numerical solutions are inherently approximate. It also has got certain amount of error. But then again, it is also possible to reduce the error. If I subdivide the interval and make it half, then you can see that according to the extended slope, the solution would be somewhere around here for an intermediate point, which is half of xf. And here you can see that the error is certainly reduced. I can go on subdividing the interval like this. If I can break it apart into sufficiently small domains or small steps, then I can obtain a good enough approximate solution, which would be an appropriate substitute for the exact solution. This is basically the Euler method. What we have highlighted here in this graph is the essence of the Euler method. We'll discuss the Euler method in detail in just a little bit later. So it is always a good idea to discretize the domain or zone of solution. So the first step always in obtaining a numerical solution of an ODE is to partition the interval x0, xf on which the solution is required. We divided this region x0, xf into a finite number of subintervals, which is represented by the points x0, x1, x2 going up to xf. Obviously, the x0 and xf points are the extremities. x0 is the initial one, xf is the final one. And in between, we obtain these mesh or grid points represented by x1, x2 going up to xf minus 1. So here is the initial and the final point, and the zone of solution is divided like this into a finite number of subintervals. So these are the mesh or grid points. This is known as the mesh or grid spacing or the step length. The step length can be expressed as follows, where hj, which is the jth step, is equal to xj minus 1. So that is the x coordinate values of the subinterval jth subinterval and j minus 1th subinterval. So if j varies from 1 to f, then we can get the step length for each of the individual subintervals. To make the matters more simple, we more often than not consider uniform spacing, which means that aj will be equal to a constant. So aj is equal to z. h. And this can be represented as follows. So xj would be equal to x0 plus jh, where j varies from 0 to f. And in numerical solution of an ODE, we look for a number yj, that is the y coordinate, which is an approximation to the value of the solution yx at the point xj. And once that is determined, we move on to the next step. And in that way, we actually build up a set of values for yj's corresponding to given xj's. So this is what we are looking for in terms of the numerical solution of the ODE. The set of numbers yj, that is starting with y0 going up to yf, is the numerical solution of the initial value problem. At all of these points, x1, x2, x3, like that, we will get a value of the y coordinate. So here at x1, somewhere around here, we will get y1. At x2, we'll get y2. At x3, some value will be obtained. Like that, starting with x0, of course, x0 is a given value. This is the initial point. Starting with that, using the slope, we'll obtain all these y coordinates and ending at yf. So basically, this is giving an indication of a curve like this. And remember that we are basically looking for a solution curve, which is gx as the solution of the initial value problem. I hope up to this is clear to you. Is that okay? Okay, we'll move
Yes,
forward. Okay, we'll move forward. Let us now discuss about one of the simplest extrapolation techniques through which we can obtain the numerical solution of an ODE. And this is known as the Euler method. As already said, this is probably one of the simplest methods and uses a very simple extrapolation technique for developing a solution. We will look at the solution of an ODE given in this form. So dy dx is equal to f of xy. F of xy is, of course, a general function. And this ODE is to be solved for a given initial condition of yx0 equal to y0. So value of y at x equal to x0 is given, and that is y0. Let us first of all try to understand what this method does graphically. So we have the xy plane over here, and we also have indicated the zone of solution or the region where this solution of the ODE is to be obtained, and that is x0 to xf. What else is known to us is this initial point, because it is an initial value problem. The initial point x0, y0 is given to us, which indicates that the solution curve is going to start from this point. Not only that, what is also known is that at the starting point, it is going to have the slope given by f of x0, y0. The given ODE is dy dx equal to f of xy. So if we can put the value of x0 and y0 in the function given by f of xy, we get a value of dy dx, and that is basically the slope at the starting point x0, y0, represented by this arrow. That is the slope. So we know where the solution curve starts and what is its slope. That means it moves in which direction at that initial point. With that, we are looking to develop the next points. The next point on the solution curve is to be extrapolated by taking a small step in the direction indicated by the slope. So let's say this is the small step h that takes us from x0 to x1. If we extend the slope, the line indicated by the slope, that is going to intersect with the vertical line passing through x1 at the point indicated by the blue dot. And at that point, the y coordinate is y1. We have extended it to the vertical axis, as you can see with through that blue dashed line, and the y coordinate of that particular point comes out to be y1. So now we know x1, y1. The second point is known. What would be the value of y1? y1 would, of course, be equal to y0 plus h into the slope. We know that slope is usually given by, in coordinate geometry, something like this. That is basically the formula of slope. Here you can see, if I manipulate this, it will be y1 minus y0 divided by h, which is equal to f of x0, y0. That is the slope at the initial point. What is h? H is nothing but x1 minus x0. So that gives us the slope like this. So that is what has been expressed through this formula. Now you have to consider what is known on the right hand side. Is y0 known? Yes, of course. We are told what y0 is here. Do we know h? Of course, h is under our control because we control the step size. So we know h. It has to be a small enough number. The function f of xy, is it known? Yes, of course it is known because we are given the ordinary differential equation. So, of course, f of xy would be known to us. We also know x0 and y0. So the given value can be input or plugged in into this function to obtain the slope. So everything on the right hand side is known to us. So it is just a matter of calculation to obtain this y1. If we obtain this y1, then we know this second point. x1 is known, y1 is known. So we have calculated the next step or the next coordinate in the solution curve. Now we can repeat the process and similarly proceed from y1 to y2. So what we'll do, we'll step or move forward in the right direction by amount h. At this location, we know the coordinate, that is x1, y1 is already known from the previous step. And if x1, y1 is known, then we can get the slope at that point. Again, we'll use the ODE, the given function, plug in x1, y1 into this function, obtain the slope. And once the slope is obtained, we can extend it to get the next point. So that way, x2, y2 is obtained. And then we can repeat the process continuously till we reach the right side domain or right side extremity xf. So in the next step, y2 is given as y1 plus h multiplied by f of x1 y1. Look at the right hand side, everything is known. We can pretty easily calculate y2 and then move on to y3 and y4 like that. So this is a very simple technique that gives us an approximation of the solution. So if you have to generalize it for j plus 1th point, we can write the formula as follows. This is the general formula for Euler method. Yj plus 1, that is the j plus 1th point, is equal to yj, is y coordinate at the jth position, plus h step size multiplied by f of xj yj. On the right hand side, everything should be known. So very easily you can calculate the value of yj plus 1. If you compare it with the exact solution, you will see that there would be some error in the solution because it is an approximate method. And the error is indicated by the difference between the exact solution and the approximate one that we have obtained. So that is the difference. The difference is the error in the solution. So this method is basically a technique for developing a piecewise linear approximation of the solution. We are approximating a solution curve, which may be a smooth curve, by breaking it apart into a series or sequence of segments of straight line. And these straight lines are the ones that we have obtained here. So these are the segments of straight line that is used to approximate the solution curve. Needless to say that if you reduce the step size, make h smaller, then you will require more number of straight lines, but it will give you a more accurate solution also. We have to consider, of course, what kind of error is present. I have already mentioned that error is inherent in these numerical solutions, and error in the formula that is given here for the general form of the Euler method is of the order of h square. You can see that the error is basically h square by 2 multiplied by y double dashed z, where z is a point, any arbitrary point in the region of computation. That means within x0 to xf. The question is, how do we get the indication of the error? For that, we need to consider the Euler method from the perspective of Taylor series expansion. We have to assume that the function yx, it can be expanded through Taylor series in the closed interval of x minus h to x plus h. And if we do that, we can write yx plus h as equal to yx plus h by 1 factorial y dashed x plus h square by 2 factorial y double dashed x, like that going up to infinity. So the pth term, the general term, would be minus 1 to the power p h to the power p by p factorial y px, where ypx is the pth derivative. In this series, in this expansion, if we consider only the first two terms, that is yx plus h by 1 factorial y dashed x, and club together all the other terms in as order of h squared terms, then we can write it like this and manipulate the terms in such a way that we have y dashed x is equal to yx plus h minus yx divided by h, and with y dashed x you have all the order of h squared terms. If those terms are neglected, we obtain an approximation of y dashed x at x equal to xj, and that would be equal to y dashed xj is equal to yj plus 1 minus yj divided by h. You will probably remember the term truncation error. What is truncation error? It occurs when we truncate or terminate an exact mathematical procedure. The exact representation of yxh is this infinite series of terms. We are truncating after two terms here and representing it approximately like this. So that is going to obviously incorporate some error in the solution, and that error is the truncation error. In the previous slide, I mentioned that the error in Euler method is of this form. Where j is any point in the domain of solution. That means x varying from x0 to xl. And you can probably see here that that term is basically this term. That is the highest term in this series. So h squared term. That is why it is said that the error in Euler method is of the order of h square. Now we can take this forward, this derivation forward, and use this representative ODE that we have been covering in the previous slides. That is dy dx is equal to f of xy. Then at point xj yj, we can write the function as f of xj yj. And if we replace that in the previous approximate expression, then it gives us the same expression that we derived in the previous slide from the graphical representation. So yj plus 1 would be equal to yj plus h into f of xj yj. So this is the formula for Euler method. It's a very simple formula. In fact, it's a very simple technique, and it can be applied to the different mesh or grid points, that is xj, j going from 0 to f, to get the numerical solution like this. So first you obtain y1, which will be y0 plus h f of x0 y0, then y2, then y3, like that you go up to yf. So that is basically the Euler method. Now let us consider an example for this Euler method. Although it's a very simple method, I think by doing this problem, it can be the concept can be made much more clear. So what is the problem? We have to solve the following ODE given by dy dx plus xy equal to 0. The solution interval is provided to us, that is 0 to 0.25. The initial condition is also given, that is y at x equal to 0 as a value of 1. So we apply the Euler method in this interval. Now, what is missing from this problem statement is the step size. We can select an appropriate step size. Let us say that we'll choose an h of 0.05. So the step size is h equal to 0.05. By the way, what is the function here? F of xy here is given as minus xy. Remember that our representative ODE was in this form. So here dy dx is equal to minus xy. So f of xy is given by minus xy. And what is the Euler formula? Yj plus 1 is equal to yj plus h into f of xj yj. So we'll repetitively apply this formula in order to get the solutions, approximate solutions.
Sir,
Yes.
Euler method is basically confined with first order only.
Yes.
Okay, sir.
This is a first order method. And that's why the error would be higher here. At x equal to 0, we are provided this value, y equal to 1. This is the initial condition. So we can, to be familiar with the representation, we can write it like this. So x0 is 0, y0 is 1. So what would be y1? This is equal to y0 plus h into f of x0, y0. This is 1, we know. H is known to us. We have to find out f of x0, y0 minus x0, y0. x0 is 0 multiplied by 1 becomes 0. So we can now substitute the values. This is 1. Sorry. This is 1 plus 0.05 multiplied by 0 gives us 1. So y1 is now obtained. y1 is 1. So what is this point? The next point in our solution, x1, y1 is basically 0.05, 1. With that value, we can go to the next one. So we go for y2. And this is going to be y1 plus h into f of x1, y1. That is y1 plus h into f of, okay, let me just write it as minus x1, y1. y1 is known, that is 1. This is 0.05. What is x1? x1 we have got here. So if you calculate this, it's probably going to come out as 0.9975. So that gives us y2. Similarly, now we can go for y3, which will be y2 plus h into f of x2, y2. x2, y2 is already known from here. x2 is 0.05 and y2 is 0.9975. Sorry, x2 is equal to 0.1. So if we input those values in this function, we'll be able to calculate that, and we continue to do these calculations till we find the last y value that is corresponding to xf. So yf, once it is found out, you will see that you have got a solution. You can represent this solution in a tabular form as well. So if you have this table at 0, this is given as 1. That is the given condition. At 0.05, we have obtained this as 1. You can see it here. At 0.05, we have obtained it as 1. In the next one, this is 0.1, 0.75, and like that, it will continue. Now, the question is, how close is this to the actual solution, the exact solution? Can anybody tell me what would be the exact solution for this expression, this ODE? Can you carry it out? dy dx plus xy equal to 0. What would be the actual solution?
Yes, understood.
Yes. Take your time. Tell me the value. You can separate out the variables. So dy by y would be equal to minus x dx integrated. So y would be equal to e to the power minus x square by 2 plus c constant.
Yes,
The
yes,
constant can be evaluated from the condition that is
C0.
from this condition.
C to 0 আসছে।
Yes, if you put this condition over here, this c would come out to be 0. So basically, the exact solution is y is equal to e to the power minus x square by 2. If we put x equal to 0, obviously, y would be equal to 1. But in the next case, x is equal to 0.05. So e to the power minus 0.05 square by 2, that should not be equal to 1. It may be very close to 1, but that's not equal to 1. If you put it into the calculator, which I have done already, you will get a value of 0.999, something like that. So basically, that's where the error comes from. Euler method may provide you with a stable solution. There is, of course, a condition for stable solution, but we will not at the moment go into that. But errors will be there. And the error will build up as x increases. Because consider this, that we are starting with a point which already has got some error. x1, y1 is not exactly on the solution curve. It is slightly removed from that. That is represented by the truncation error. And on the basis of that erroneous, although it is small on this erroneous point, you are calculating the next point. So basically, as you go forward with the x, as x increases, errors will build up. They will get accumulated. So that is why this Euler method, although it is a very simple method, is not used in practical scenarios. It is not that popular. One of the most popular methods is the RK series of method or Runge-Kutta methods. Now, if you are honest about it, you can probably write a whole book about the Runge-Kutta methods. These are a family of iterative methods used to approximate solutions of ODEs. But of course, we cannot go into such amount of detail. What we'll look at from the graphical perspective is the second order RK method and the fourth order RK method. Again, the mathematical analysis of this, I'm not going to touch upon. If you are interested in it, you can go to any standard numerical analysis or mathematics textbook where it will be explained in detail. Here, for this class, we'll just look at how these two methods actually obtain the solutions from a graphical perspective. And on the basis of that, we'll try to establish some algorithm, develop some algorithm which, when implemented, would give us the approximate solution of initial value problems. If we compare this RK method with the Euler method, the difference is quite clear. In Euler method, the information about the slope or the derivative of y, that is dy dx, at a given point is utilized to extrapolate the solution and obtain the next point on the grid. That is the next solution on the grid. So basically, we are using the slope at a given point, at a single point. The information about slope at a given single point is utilized. In contrast to that, in RK methods, we judiciously use the information on the slope at more than one point. And on the basis of this information of slope about multiple points, we extrapolate the solution to the next step. So what is the difference? In Euler method, single point slope is used, whereas in RK methods, multiple points, slopes at multiple points, I should say, are utilized to obtain the next solution. So basically, we can say that the general formula for this series of methods or class of methods, RK methods, is like this. Yj plus 1 is equal to yj plus h multiplied by the average slope. Now, this average that is taken is more often than not a weighted average. If we are to write down stepwise what is done in these class of methods, it would be something like this. So the underlying principle of RK method is that, first of all, slope at a point xj is calculated. But not only that, we calculate the slope at several other points. We are not limited to a single point xj. Once that is found out, a weighted average of these calculated slopes are obtained. So that means if we have n number of points on which the slopes have been calculated, all these points are provided with some weight. Not all the points would be having the equal weights. Some may be having smaller weights or some may be having larger weights. So it is going to be multiplied by some factor. And that weighted average is then multiplied by the step size, and the result obtained is added to yj to obtain an estimate for yj plus 1. So this is the underlying principle of the RK method. This is what is done in all of them. What is different is that how do we obtain the different points, those multiple points and their corresponding slopes. So basically we can write it like this. This is the general formula for RK method, where yj plus 1 is equal to yj plus h multiplied by summation of n varying from 1 to v pk, or we can say bn kn. Here n is basically indicative of the number of points that we are going to consider. So if n varies from 1 to v, that means in this particular general situation, we are going to consider v number of points and slopes at those v number of points. All those points would be given some weightage indicated by this term over here. This is the weighing factor. These are the slopes. And it indicates number of points. So if v is equal to 2, then this summation would be b1 k1 plus b2 k2. The slopes at the 2 points are k1 and k2 respectively, and the weight factors at those 2 slopes, at those 2 points, are b1 and b2. The weights are given in such a way that summation of bn, n varying from 1 to v, that is always equal to 1. As I said, if we consider 2 number of points, that is n varying from 1 to 2, that makes it a second order RK method, and it is represented by RK2. Similarly, if n goes from 1 to 4, then it is a fourth order Runge-Kutta method, RK method, and it is represented by RK4. So that is basically the RK method in general. Now let us talk about the second order RK method, which is also known as the Hewn method. The ODE that we have taken up over here is the same as before, that is dy dx is equal to f of xy, where the initial condition is given as y equal to y0. As already mentioned, we'll look at the graphical perspective, and here you can see the xy plane and the initial point x0, y0 represented in red. The next step over here is, of course, x1, that is at a distance of h from the initial point. So x1 would be given by x0 plus h. So what are the things that are known to us at this point? Obviously, the initial position from where the solution curve starts, and the slope, which can be calculated as S0 equal to f of x0, y0. On the basis of the information available, what we do next is we draw a straight line starting from x0, y0 with a slope of S0. This is the straight line which intersects with the vertical line drawn through x1 at a point y1 bar. You can see y1 bar over here. We have extended it horizontally to the y-axis, and that is the y1 bar. Next, we will determine the slope at this point, that is x1, y1 bar. Can we determine pretty easily because we know the formula for the function f of x1, y1 bar. We know the coordinates x1, y1 bar. We plug it into the form of the function and get the slope like this. So that is the slope S1. This is the second point that we have considered. Next, we will calculate the average slope. So the average would be S0 plus S1 divided by 2. With this average slope, starting from the point x0, y0, we will draw a line which intersects with the vertical line passing through x1. This is basically our next point in the solution curve, that is the approximation of y1. So what we have done? We have first of all obtained the average slope. How do we get the average slope? We get two different points. One is already known, that is the initial point. And from that initial point, using the slope S0, we have got another point y1 bar. But this is not the solution. Here, what we are interested in is the slope at that point. So we have calculated S1. Now we have got 2 points, S0 and S1, 2 slopes. Calculate the average of this slope. And then finally, from the initial point with the average slope, we extend a line to the vertical line passing through x1. The intersection between the average slope line and the vertical line at x1 gives us the approximate solution at that position. This is the approximate estimate. So basically, we can write it like this. So y1 would be equal to y0 plus h multiplied by the average slope. That is the general formula. If you are to generalize it, then of course, we'll write it for the j plus 1th step corresponding to the jth step. So yj plus 1 would be equal to yj plus h by 2 multiplied by sj plus sj plus 1. Now what is sj and sj plus 1? They are the slopes at the two different points. They are expressed as shown here. So you can just check with these expressions by putting j equal to 0. So here, if you put j equal to 0, you will have y0 plus h by 2. This is s0 plus s1. And of course, this will be y1. So that actually makes it equivalent to this expression. But this is the general one. This is the general expression. And what is S0? S0 is basically f of x0, y0. That is what we have calculated over here. And what is S1? This is f of x1, comma, y1. Y1 here has been expressed as yj plus hsj, because we know this is y1 bar, that will be equal to y0 plus hs0. That is basically an equation of this line. It starts from y0, goes up to y1. The x coordinates are x0 and x1. So this is the formula for the Hewn method or second order RK method. Any questions from here?
No, sir.
Okay. So let's move forward and try to solve this problem. This is the same problem that was given for the Euler method, and you can see the same OD dy dx plus xy equal to 0, and the initial condition y0 equal to 1. It has to be solved in the same interval, that is from 0 to 0.25. And we can simply apply the technique that was developed in the previous slide. Let's at least try to do one step of this problem in order to clarify the thing. So let me just write it over here. Dy dx is given as minus xy as per the problem statement, which implies that f of x comma y is nothing but minus xy. Initial condition is x equal to 0, y equal to 1. That is already given. And the formula that we will be looking to apply for RK2 is yj plus 1 is equal to yj h by 2. Let me write it as S0 and S1. I'm not going to change the subscript of this to avoid confusion and make it much more clear. So what it means is that we have the two boundaries like this. Let's say this is xj, yj. That is the known point. And on the basis of the known point and the slope, this slope let us represent as S0. We are calculating the unknown point over here, which is xj plus 1, yj plus 1. And this is S1. So once we get S0, slope on the left hand side, and S1, the slope on the right hand side, we can get the average slope and draw a line with that average slope from there, and that would give us the actual solution at this point. That is the approximate solution, of course. So let us start with this given values. S0 would be dy dx at this given point x0, y0. Basically, that makes it minus x0, y0. 0 into 1 gives us 0. What about S1? That is dy dx x1 y1. By the way, according to our graphical representation, this was y1 bar. But for this problem, let us just write this as y1. Okay, to avoid confusion, let us put this bar over here. So this is minus x1 y1 bar, and that would be equal to minus 0.05 multiplied by 1. How do we get y1 bar as equal to 1? y1 bar is equal to y0 plus the step size multiplied by the slope at that point, s0. So s0 is obtained as 0, so that part is 0. y0 is 1, so y1 bar is also 1. So that gives us minus 0.05. The average slope is, of course, half of S0 plus S1. That is half of 0 plus minus of 0.05. We get minus of 0.025. That is the average slope. So now we can use this formula. Y1 would be equal to Y0 plus H, step size, multiplied by the average slope. This is 1 plus 0.05 multiplied by minus 0.025. We get a value of 0.99875. We can approximate towards 999. So this is the end of the first step. And the solution that we have obtained at this step is x1 is 0.05, y1 is 0.999 approximately. If you think back to the Euler method, you will probably remember that at the end of this particular step, we had obtained y1 as equal to 1. And I had mentioned that for the actual solution, where we have actual solution as e to the power minus x square by 2, if you put 0.05 over here, you will not get y equal to 1. Close to 1, but not exactly equal to 1. So quite simply, RK method is more accurate as compared to the Euler method. If you think of it in terms of the Taylor series, it can be proved that its accuracy is based on the less number of terms being neglected from the series. And it can be proven that the error in this RK2 method is of the order of h cube, whereas for the Euler method, it is in the order of h square. However, again, this mathematical analysis of the error we will not look at in the present class, and I leave that up to you to read it from the book. What is in our interest is, of course, development of a code. We need to develop a working code to implement RK2 method. And this can be done quite simply using the graphical understanding of the procedure of this Hewn method. If you want to write an algorithm for this, we can develop it in the following way. So we have this domain x0 to xf. Within this domain, we are looking for a solution of a first order ordinary differential equation with a given initial condition. The first step in this algorithm is, of course, reading of the inputs. So what kind of inputs would be required? First of all, the initial condition is to be given. So this point x0, y0 must be known. So let me take the input as xi, yi. Although it is written as xi, yi, basically we are taking the input of x0 and y0. So this is the input of the initial condition. What else is required in terms of input? The step size, of course. What would be h? So we need to read that as well. So read h, which is step size. Anything else? We need the final position as well, xf. That is not yet has been read. So and xf, that is, we can say upper bound of the solution domain or solution region. x0 has already been read, so the initial position is known. We have to know the final position. That can be read as input. So that completes the input part. Here we will take the while loop, make use of the while loop. Previously, I have told you to avoid while loop because it might create a possibility of an infinite loop if particular termination criteria is not satisfied. However, here we provide the while loop in such a way that it is not going to create that kind of a problem, because here xi is less than equal to xf, this condition is checked. Now this is going to be satisfied at one point of time or other, because at the end of each step we are adding the step size h with the previous one. So basically it is monotonically increasing, and h is not changing due to any kind of manipulations or calculations. So after a certain finite number of steps, xi is going to reach xf, and that is guaranteed. So due to that, we have used this while loop. While this condition is satisfied, the following steps are to be performed. By the way, we can definitely use a for loop as an alternative. But in that case, you will require how many number of times this loop has to run. That can also be calculated. It's not a problem because you already know what is x0 and xf, and you know the step size. So from these input parameters, you can calculate how many number of times this for loop is going to run. So this can pretty well be an alternative to that. Also, you can change the input parameters just a little bit and directly read how many number of subintervals are to be created. And that obviously gives you an idea about how many number of times the for loop is going to run. But then again, if you read the number of subintervals within the solution domain, then you need to calculate the step size. That is not a difficult issue, of course. You know xf and x0 You also know the number of subintervals or steps can be calculated from there. The step size can be calculated from there. So those are just variations of in terms of the input parameters. But here, once we start the while loop, the first task we'll do is we'll print. I'll not write printf, I'll just simply write print xi yi. Previously, I have used the index j in discussing about this, but as I have already started writing I, let's not complicate matters and continue with this index of I. Next step, calculate the slope as 0. So you have f of xi, yi. Xi, yi are known, so obviously you can calculate the slope. Then get xi plus 1, that is the next step, which is xi plus the step size h, already known, so you can get that. Then yi plus 1, this is going to be yi plus s0 into h. By the way, this is not the solution. Remember that this is where we are getting the next point in which to calculate the slope. So number 8 is that particular slope s1. This is going to be f of xi plus 1, y plus 1. Now we have got two different slopes, s0 and s1. We'll calculate s average, which is in the next step, we calculate the approximation. That is yi plus 1 would be equal to yi plus h into the average slope, which we have obtained here. So this is the next approximation. Once we have obtained that, we'll simply store xi plus 1 in xi and yi plus 1 in yi and go to the start of the while loop. At the beginning, we'll check xi, whether it's less than xf or not. If it satisfies, we'll go inside this. And at the first step, you will write xi, yi. So that was the starting point of the solution. With respect to that, we'll again repeat all of these steps, and when it's completed, that means when xi becomes larger than xf or equal to xf, sorry, when it becomes larger than xf, you will stop the program. So that is the final stoppage. So this is a very basic algorithm for implementing second order RK method. One thing that I have not mentioned previously is that the weight. See that this is having the same weight at both the positions. So B1 is 0.5, B2 is 0.5. So it works like a simple average. But in the next method that we will consider, the weights will be different. I'll just very quickly go through this. We'll not discuss too much about this, but obviously the graphical representation is important, and that would help you in developing the algorithm for the code. This is probably the most popular solution technique for ODEs. That is the fourth order RK method, Rangekatta method. You can probably guess that as it is a fourth order method, it is going to use slopes in 4 locations, 4 points. Let us see what are those points. we have the same xy plane. The initial point here is represented as xi, y, not x0, y0. That is just a general representation. And you can consider that it is any general intermediate step. Even if it is the first step, it is going to work in the same way. So the initial point is known. We have now the interval h, but this interval h itself is again divided into two parts. So there is a midpoint of this interval, which is indicated by the point xi plus h by 2. So the total interval is h. We have the indication of the midpoint of that interval over here. That is obviously at a distance of h by 2 from xi. At the initial position, we have a slope k1. This is known. K1 is basically f of xi, yi. Because the point xi, yi is completely known, we know the slope k1. Basically, if you put xi, yi in the function, the functional value would supply you with k1. Extend this slope to the midpoint of that interval. So the vertical line passing through the midpoint of that interval gives us the next slope. At this point, we'll also calculate the slope, which is known as k2. Here, what you have to supply? The coordinates of the point indicated over here in red, and the coordinate at this point is basically xi plus h by 2. That is the x point over here. You can see that is the midpoint, comma yi plus k1 into h by 2. That is the equation of this straight line. This is yi. We are adding to it the multiplier k1 into h by 2. K1 is the slope, h by 2 is the step size here. So we arrive at this point. So that is the coordinate of this point. If you supply the coordinate of this point into that function, you will get slope k2. Now with this k2, we draw a line from the previous point, that is xi, yi. Extend it like this, and at this point calculate k3. So we know the coordinate of this particular point over here. This coordinate is known, and if you supply that coordinate to the function over here, you will get this slope k3. In the next step, we are going to use k3. Go back to xi, yi. With k3 as slope, draw this line. Now this one goes to h, not h by 2, not the midpoint of the interval, but to the end of the interval. Intersection of this extended slope and the vertical line, that coordinate point is known, and we can calculate another slope at that point, that is k4. So we have obtained 4 different slopes, k1, k2, k3, and k4. This is a 4th order method, so we have to use 4 different slopes at 4 different points. So these are the 4 different slopes that will be used to calculate the average slope. This is a weighted average, by the way. And you can see that the weights are not equal. The first point that has an weightage of 1 by 6. The second point has a weight of 1 by 3. Third one has 1 by 3. Fourth one has 1 by 6. So K2 and K3 have higher weights as compared to K1, K4. That is just specific to this RK4 method. With this average slope, from the known point xiyi, we'll draw a line which intersects with the vertical line through xi plus 1 at xi plus 1, yi plus 1. That is the approximate solution for the step xi plus 1. So yi plus 1 would be obtained as yi plus h multiplied by the average slope. Average slope has already been obtained, which is Ka average, and you can utilize that to get y plus 1. So this is the final form of the fourth order Runge-Kutta method. Can be written like this as well, where this Bn is basically the weights represented here. This is B1, B2, this is B3, and that is B4. K1, K2, K3, K4 can be calculated through these expressions. This particular method, RK4 method, is quite accurate. It has got error of the order of h to the power 5. If you derive the formula following Taylor series expansion, you'll see that the terms after the h to the power 4 term, that means starting from h to the power 5 term, that is neglected. Those terms are neglected. So that is why the error in this particular method is of the order of h to the power 5. If h is small enough, then RK4 method is pretty accurate. And that is why this is one of the most popular methods in solving initial value problems. So that is all for today's class. I would request you to try to develop a C code for the Hewn method, that is RK2 method. You can also write down an algorithm for the RK4 method. You can also try to implement that algorithm as a code in C for RK4 method. As practice, you can also try to develop algorithms and codes for the Euler method also, but that particular method is not that useful in terms of getting accurate result, because that usually has some substantial error in the approximate solution. So the best bet for obtaining approximate solutions for initial value problems is the RK4 method, and you should try to develop programs for that method also. So that's all for today. Thank you. Okay. Questions? Any questions? No.
হ্যাঁ স্যার, মানে ওই সিলেবাস রিগার্ডিং একটা মানে কোশ্চেন ছিল যে আপনি ওই
বলো।
আমাদের যে সিলেবাসটা মানে ইউনিভার্সিটি থেকে দিয়েছে ওখানটা দেখলাম স্যার এই গস সেডেল মেথডটা মানে ইটারেটিভ সলিউশনে নেই, কিন্তু ওটা দেখলাম যে আপনি করিয়েছিলেন ওইটা। আর স্যার এই মেথডস অফ ইন্টারপোলেশন আর নিউটন ফরওয়ার্ড এলিমিনেশন সরি ফরওয়ার্ড ডিফারেন্স এন্ড ব্যাকওয়ার্ড ডিফারেন্স, এই দুটো কি মানে আপনি কি মানে এটা করাবেন না এই পার্টটা? বা
এই পার্টটা প্রবাবলি সময় হবে না, কারণ নেক্সট ক্লাসটা হচ্ছে প্রোগ্রাম ইমপ্লিমেন্টেশন অফ দিস অয়েলার মেথড এন্ড আরকে মেথড। এগুলো তোমাদের নেক্সট ক্লাসে করতে হবে। নেক্সট ক্লাস মিন্স টুডে ইজ 7th, so 14th is the last class of this semester. Right? So then we have the
রিকোয়েস্ট ছিল মানে আপনি স্যার মানে এই যে কয়েকটা মেথড বাকি আছে, যেমন ধরুন এই দুটো বললাম, তারপর এই ম্যাট্রিক্স ইনভার্সন ইউজিং গস জর্ডান এলিমিনেশন, আর ওই কম্পিউটেশন অফ ডেরিভেটিভস ইউজিং নিউটনস ফরওয়ার্ড ব্যাকওয়ার্ড সেন্ট্রাল ডিফারেন্স ফর্মুলা, মানে ওই ডিফারেন্সিয়েশনের যে পার্টটা, স্যার এই কয়েকটা জিনিসের আপনি ওই রেকর্ডেড লেকচার করে দিতে পারবেন? মানে আপনি বলছেন
I'll try but for interpolation what we have already done, I think that's good enough, but let me see what I can do. Otherwise you can of course take help of any standard textbooks, read the topic. If you have any problems you can directly get in touch with me, not only with in this semester, later on also. If you have any kind of queries regarding those topics, you can come to me. I will try to explain.
Okay sir.
Okay. So developing recorded lectures, it takes a lot of time. In fact, developing the PowerPoint presentations also takes time. So I don't know whether I will be able to invest that much time once the semester gets over, because I will have to check copies and check the assignments that you have submitted. So those are there. Based on that, I'm not sure whether I can give you such recorded material, but definitely I will try. And if not possible, then you can come to me at any time with any kind of queries regarding these topics, and we can discuss about them. Okay.
Okay sir.
Okay. And just you will also have your test on 21st. Okay, 21st during the class time. That means from say 11 to 1, 2 hours.
স্যার মানে সিলেবাসটা ওই আপনি 14th এ লাস্ট যেটা করাবেন সেই অবধি, তাই তো? মানে কম্পিউটার ইমপ্লিমেন্টেশন।
Yes. That is going to be the complete syllabus.
স্যার এই মানে মডিফাইড ইউলার্স মেথড এটা তাহলে থাকবে না?
No.
ওকে স্যার।
যেগুলো পড়ানো হয়েছে ক্লাসে, only those will be included in the test.
ওকে স্যার।
ওকে। হ্যাঁ, কেউ কিছু বলছিলে?
হ্যাঁ স্যার, বলছিলাম ওই যে অটোকেডে যে তো ওখানে মানে কি বলবো, যে যখন ডাইমেনশন গুলো করছি, তো ডাইমেনশনে মানে মাঝখানে তো লেখাটা আসছে, ধরুন আমার 30 সেমি, তো মাঝখানে দিয়ে ওটাকে যদি আমি একটু নিচের দিকে করি, ওটা কোনো করা যাবে ওইটা?
বুঝলাম না, নিচের দিকে বলতে?
নিচের দিকে বলতে যখন আমি ডাইমেনশন লিখি তখন একদম মাঝখানে মানে ওই যে দুটো তীর চিহ্ন দুদিকে যাচ্ছে, তো মাঝখানে 30 লেখাটা আসছে, তো আমি একটু বাম দিকে লেখাটাকে করতে চাই, ওইটা করা যাবে?
You can do it. Just go to properties, ওখানে দেখবে offset x values, offset y values, এরকম কিছু অপশন আছে।
আচ্ছা বুঝতে পারছি। হ্যাঁ ঠিক আছে।
ওখানে তুমি তোমার মানে ওটা হয়তো একটু তোমাকে এক্সপেরিমেন্ট করতে হবে যে এক্স্যাক্টলি কোথায় দিলে তোমার সুবিধা হচ্ছে। That can be done from there.
আচ্ছা স্যার, আর একটা কথা হচ্ছে ওই কি বলুন তো, ব্যাপারটা হচ্ছে যে আমি যখন মানে ওই ডাইমেনশন গুলো লিখছি, তো ওখানে লিনিয়ার ডাইমেনশনটা একটা ছবিতে আছে, তো ওটা ফাই লেখা আছে, মানে কি বলবো, মানে ব্যাসটাকে দেখিয়েছে, কিন্তু ওটা কি আমি ফাই হিসেবে দেখাবো না শুধু লিনিয়ারটাই দেখাবো?
না, তোমাকে যেহেতু তুমি সার্কেলের ডাইমেনশন দিচ্ছ, you have to provide the notation phi. ওকে,
আচ্ছা।
তো এবার ফাই কি করে লিখবে? ফাই তো তোমার কিবোর্ডে নেই, সেটার জন্য তোমাকে যেটা করতে হবে সেটা পার্সেন্টেজ সি।
হ্যাঁ, ওটা বুঝতে পেরেছি, কিন্তু দাঁড়া স্যার আমি প্রেজেন্ট করছি তারপরে বলছি
হ্যাঁ
দাঁড়ান।
হ্যাঁ
Present করছি।
স্যার আমি এতদিন আপনাকে ওই প্রবলেমটা বলছিলাম যেটা আমি আর সত্যম দুজনেই ফেস করছিলাম, ওই ইয়ের একটা সার্কেলকে ট্রিম করে দেওয়ার পরে ওর ডাইমেনশনটা মানে ডিফারেন্ট চলে আসছিল, মানে
হ্যাঁ।
ওটা বুঝতে পারছিলাম যে কেন ব্যাপারটা হচ্ছে।
ঠিক আছে, তুমি এক এক করে প্রেজেন্ট করো, ঠিক আছে?
ওকে স্যার।
কোথায় এই তো স্যার দেখতে পাচ্ছেন?
হ্যাঁ দেখা
হ্যাঁ
যাচ্ছে।
এই যে মানে এখানে যে 525 লেখা আছে, এটাকে আমি 5 লিখবো না শুধু 25, মানে এই যেরকম 25 আছে ওইরকম লিখে দেবো?
না না,
মানে এখানে তো
525 লিখ, 525 লিখ।
আচ্ছা আচ্ছা, মানে আমি ভাবলাম প্রথমে একটা তো
That is-
মানে ডাইমেনশন তো
না
লিনিয়ার
না
ডাইমেনশন
না, লিনিয়ার ডাইমেনশন হলেও the part
আচ্ছা
that you are indicating is a circular part, ঠিক
আচ্ছা
আছে?
আচ্ছা ঠিক আছে। হ্যাঁ, আর এখানে যেমন 545 থেকে একটু নিচের দিকে লেখা হয়েছে, এই কথাটাই বলছিলাম যে এটা তো আমার মাঝখানে চলে এসেছে, তো এটাকে আমি নিচের দিকে করতে
এটা
পারবো।
তুমি করতে পারবে,
আচ্ছা আচ্ছা।
that you can do.
হ্যাঁ, কিন্তু স্যার আপনি যে স্ট্যান্ডার্ড হিসেবে দিয়েছেন, ওর মানে ওর রুল কি বলে কি মানে মাঝখানে লিখতে, ওই যে স্ট্যান্ডার্ড ডাইমেনশন ফলো করতে বলেছেন?
না না, মাঝখানে লিখতে হবে সেটা নয়। তোমার যখন এখানে দেখো, তুমি যদি এখানে যদি মাঝখানে লেখো তাহলে
হ্যাঁ
তোমার ইট উইল ওভারল্যাপ উইথ দি হ্যাচিং পোর্শন,
হ্যাঁ
রাইট?
হ্যাঁ
বাট একটা জিনিস মনে রাখবে যে আমরা কিন্তু কনভেনশনালি পার্টের মধ্যে ডাইমেনশন দিই না। উই ট্রাই টু প্রোভাইড দ্য ডাইমেনশনস আউটসাইড অফ দ্য পার্ট। কেন? তার কারণ হচ্ছে পার্টের মধ্যে তুমি যদি ডাইমেনশন দিতে যাও তাহলে অনেক সময় ব্যাপারটা কনফিউজিং হয়ে যায়। মানে ডাইমেনশন লাইন থাকবে, তার মধ্যে অবজেক্টের লাইন থাকবে, তার মধ্যে ধরো ধরো কিছু ড্যাশ লাইন আছে, সো দ্য ফিগার বিকামস ক্লামসি। So it is always suggested that if possible, you provide all the dimensions outside of the drawing figure. ঠিক আছে? এইখানে এই পার্টিকুলার যে ছবিটা দেখানো হয়েছে সেখানে হয়তো দেওয়া হয়নি, বাট it is a convention that is usually followed in machine drawing. কিছু কিছু ক্ষেত্রে তোমার কাছে কোনো অপশন থাকবে না, তখন তোমাকে হয়তো পার্টের মধ্যেই ডাইমেনশনটা দেখাতে হবে, বাট ইফ পসিবল ট্রাই টু অ্যাভয়েড ইট,
আচ্ছা আচ্ছা ঠিক আছে।
ঠিক আছে?
হ্যাঁ, আর স্যার এই যে অংশটা, এটা তো সেই মাল্টি লেয়ার দিয়ে করেছি, কিন্তু মানে এখানে যেমন তিনটা তীর ধরুন তিন দিক দিয়ে আসছে, এটা কি কোন অপশনে করা যায় বলতে পারবেন একটু?
কোনটা?
মানে এই যে ক্লিয়ারেন্স লেখা হয়েছে, আমি সেই
হ্যাঁ হ্যাঁ।
মাল্টি লিডার অপশন দিয়ে করেছি, মানে তিনটা তিন দিক দিয়ে না এরকম লিখে দিয়েছি, কিন্তু মানে এটা কোন অপশন দিলে
হ্যাঁ,
মানে
মাল্টি লিডার
একেবারে
দিয়েই করতে হবে তোমাকে, মাল্টি
হ্যাঁ
লিডার দিয়েই করতে
আচ্ছা
হবে,
আচ্ছা,
মাল্টি
আমি
লিডার
ওটা
দিয়েই।
দিয়েই করেছি।
হ্যাঁ, মাল্টি লিডার দিয়েই এটা করতে হবে, আর কোনো ইয়ে নেই, অপশন নেই।
হ্যাঁ
তোমাকে একটু এডিট করে নিতে হবে হয়তো মাল্টি
হ্যাঁ ওইটা,
লিডারে,
হ্যাঁ
তুমি
ওইরকমই করে
একটাতে কোনো
নিয়েছি।
টেক্সট লিখলে না, তারপরে একটাতেই মাত্র টেক্সট লিখলে, এরকম
হ্যাঁ সেরকম ভাবেই করেছি,
এরকম ভাবেই তোমাকে মডিফাই করতে হবে, বাট দি
ঠিক আছে।
কমান্ড ইজ মাল্টি লিডার।
আচ্ছা স্যার, এখানে যে ড্যাশ লাইন গুলো আছে, এই যে মানে এর যে ওয়েট লেন্থ আর এই যে মানে অবজেক্ট লেয়ার এই যে
হ্যাঁ,
ওয়েট লেন্থ, এটা কি সমান হবে না? আমি
না না
ড্যাশ
না
লাইনের
না না, dash line always, hidden lines or dash lines always have a line width of half of the object layer, object
আচ্ছা
line.
আচ্ছা, মানে আমি প্রথমে দেখলাম দুটো একই দেখাচ্ছে, তো এই জন্য এটা আমি একই করতে
না না,
মানে
তুমি
তাহলে কি
তুমি তোমার লেয়ারের রেসপেক্টে করবে, তোমার
আচ্ছা
লেয়ারের
আচ্ছা
রেসপেক্টে you can do that.
আচ্ছা, মানে এটা যদি মানে 0.5 হয় তাহলে এটা 0.25 হবে এর মানে ওয়েভ লেন্থটা।
হ্যাঁ হ্যাঁ
ঠিক আছে ঠিক আছে, থ্যাংক ইউ স্যার।
ওকে।
তাহলে
স্যার
হ্যাঁ বলো।
স্যার ফাইলটা তো লেখা হয়নি, আমি তো সাবমিট করে দিয়েছি।
সাবমিট করে দিয়েছো?
হ্যাঁ স্যার।
ওকে, ঠিক আছে, তে মানে খুব একটা ইম্পর্টেন্স নেই, ইটস ফাইন, ইটস ওকে।
So can you draw the arrows using polyline?
Sure, you can draw it, but of course then you will have to take a second command, text command, and with the help of the text command you have to write the text, that is clearance,
Yes.
that is written there. You have to do that.
Yes, I have done that.
Okay, that's okay, that's not a problem. Any other questions? অরণ্য কিছু একটা দেখাবে বলছিলে।
হ্যাঁ স্যার, দাঁড়ান স্যার আমি দেখাচ্ছি। স্যার দেখতে পাচ্ছেন স্ক্রিন?
শেয়ার হচ্ছে, আসছে, হ্যাঁ এসছে।
স্যার এই জায়গাটা এইটা দেখুন, মানে এটা 44 আসার কথা, কিন্তু এটা 44.3469 কেন আসছে ঠিক বুঝতে পারছি
জুম
না।
করো, জুম করো, একটু জুম করো উপরে। এখানে এখানে দেখো তোমার সার্কেলের সঙ্গে এটা অ্যালাইন নয়। দেখতে পাচ্ছ এক্সটেনশন লাইনটা তোমার সার্কেলের থেকে মিসম্যাচড, দূরে আছে।
ও আচ্ছা আচ্ছা,
ওখানে তোমার এই এন্ড পয়েন্টটা কারেক্টলি সিলেক্টেড হয়নি।
তাই কি হচ্ছে স্যার? আমি তো স্যার ও স্ন্যাপ অন করা, পরেও কেন
তোমার এখানে এখানে কিছু একটা প্রবলেম হচ্ছে তোমার।
ওখানে সেন্টার লাইনের মিড পয়েন্টটা সার্কেলের এন্ড পয়েন্টের কাছাকাছি বলে ওই মিড পয়েন্টটা সিলেক্ট হয়ে যাচ্ছে।
Probably there is something like that is happening.
এইবার আবার এলো।
তোমাকে কেয়ারফুলি এন্ড পয়েন্টটা চুজ করতে হবে। ইউ হ্যাভ টু চুজ দ্য এন্ড পয়েন্ট।
হ্যাঁ স্যার,
ওকে, তোমার একটু এপাশ ওপাশ হয়ে গেলেও কিন্তু প্রবলেম হবে ওটা।
হ্যাঁ স্যার, এবার আবার ঠিক এলো। তার মানে কিছু একটা প্রবলেম হচ্ছিল তখন।
ওইটাই প্রবলেম তোমার।
হ্যাঁ
এক্স্যাক্টলি সার্কেলের এন্ড পয়েন্টটা সিলেক্ট হয়নি।
হ্যাঁ স্যার, বুঝেছি।
প্রবাবলি অন্য কোনো স্ন্যাপ পয়েন্টে ওটা স্ন্যাপ করছে। সো ইউ হ্যাভ টু বি ভেরি কেয়ারফুল অ্যাবাউট দিস।
স্যার আরেকটা ব্যাপার, এই যে মানে এই কি বলে ফিলেটিং যে এন্ড গুলো আছে, এখানটা স্যার এই ডাইমেনশনে আমি এই যে লাল রঙের যে এটা কি বলে এই কার্ভ
এক্সটেনশন অফ দা আর্ক।
হ্যাঁ,
এক্সটেনশন অফ
এই মাল্টিলিনিয়ার দিয়ে করতে পারিস তো।
এটা কি
এটাতে কোনো অসুবিধা নেই, এটাতে কোনো অসুবিধা নেই। এটা অনেক সময় ওইভাবে দেখানো হয়।
ওকে স্যার, মানে আপনার এই ড্রয়িং
নট অ্যান ইস্যু।
তো সেই জন্য ভাবলাম এটা হয়তো মানে করতে হতো। আমি এইভাবেই সাবমিট করে দিয়েছি যদি।
ঠিক আছে, ইটস ওকে।
ওকে স্যার।
এমনি মাল্টিলিনিয়ার দিয়েও করলেও তো হয়, মানে লিখে দিয়ে ওইটা আর কি।
কিসের কথা বলছিস তুই?
ওই মাল্টিলিনিয়ার দিয়ে মানে টেনে দিয়ে লিখে দিলে R5 হলেও তো হয়।
হবে, কোনো অসুবিধা নেই।
ও আচ্ছা আচ্ছা, হ্যাঁ।
স্যার ওই ডাইমেনশন 4 যেখানটা আছে, ডায়ামিটার 4 দিয়ে ওখানে ছোট মতো, ওটার উপর একটা ছোট ট্রায়াঙ্গেল আছে, ওটার তো কোনো ডাইমেনশন দেওয়া নেই।
কোনটা বলছিস জানো না?
এই তোর আগের ফিগারটা খোল, যে ওই একদম উপরেরটা।
এইটা
হ্যাঁ, যেটা ছোট।
এটা
হ্যাঁ।
না, এটা ডাইমেনশন দরকার নেই। এটা ডাইমেনশন দরকার নেই, এটা দেওয়া
ট্রায়াঙ্গেলটা
হয়নি।
কি আঁকতে হবে? আমি ভাবলাম ওটা বোধহয় লাইনটা বোল্ড, ওই জন্য আমি ওটা শুধু স্ট্রেট লাইনটাই
না,
করেছি।
এটা দেখো, এটার হচ্ছে যে তোমার এখানে অনেক সময় একটা ড্রিল করা থাকে, ড্রিলড হোল থাকে। এবার সেটার মধ্যে অনেক সময় স্ক্রু টাইটেন করা যায়, স্ক্রু লাগানো থাকে, বা পজিশনিং এর জন্য অনেক সময় দেওয়া হতে পারে। এটা কি হয়, যখন তুমি ড্রিল বিট দিয়ে ওটাকে ড্রিল করবে, ড্রিল বিটের এন্ড দেখেছো? ড্রিল বিটের এন্ডটা অনেকটা ওইরকম পয়েন্টে। তো সেই কারণে হচ্ছে ওই ব্লাইন্ড হোল যেগুলো হয় তার এন্ডটা ওইরকম ভাবে রিপ্রেজেন্ট করা।
মানে এমনি র্যান্ডমলি একটা ট্রায়াঙ্গেল এঁকে দেবো।
ওটা ইউজুয়ালি 30 ডিগ্রি অ্যাঙ্গেলে ট্রায়াঙ্গেলটা ড্র করতে হয়, মানে তোমার ভার্টিক্যাল লাইনের সাথে 30 ডিগ্রি অ্যাঙ্গেল।
স্যার আগের দিন আমি অনেক চেষ্টা করলাম এই 6টাকে এই সাইডে আনতে পারলাম, এই 6টাকে এই দিকটা।
ওটা ইয়েটা বাড়িয়ে দে, সাইজটা, টেক্সট সাইজ বাড়িয়ে দিলে বাইরে চলে আসবে।
কিসের কথা বলছিস? ওই তোর ওই হাইটটা,
টেক্সট সাইজ বাড়ালে তোমার আবার একটা প্রবলেম হবে যে তোমার ইউনিফর্ম থাকবে না।
হ্যাঁ,
এটা প্রবলেম, ইউনিফর্মিটি লস্ট হবে। এটা ভেতরে থাকলেও অসুবিধা নেই। তুমি যেটা করতে পারো এখানে, যে এইখানে দেখো ওই ব্লু মার্কটা দেখাচ্ছে, তো মাঝের ব্লু মার্কটা ধরো, ধরে ওটাকে বাইরে টেনে দাও। মাঝে দেখো একটা গ্রিপ আছে, গ্রিপ বলতে দেখো ব্লু একটা অপশন দেখাচ্ছে মাঝে একদম, ওটাকে ক্লিক করো। হ্যাঁ, ওটাকে ক্লিক করো, বাইরে টেনে দাও।
ও আচ্ছা,
ঠিক আছে, এইভাবে করতে পারো, বা পুরো ডাইমেনশনটাকে ফিগারের উপরে উঠিয়ে নাও।
ও হ্যাঁ স্যার, বুঝেছি।
ঠিক আছে,
হ্যাঁ স্যার। আচ্ছা।
Okay, so any other questions?
No sir.
Okay, so I'll see you tomorrow again for the CAD class.
স্যার,
হ্যাঁ বল।
স্যার বলছি 3টে প্রবলেমে কি একটা মডেল স্পেস